All right, so this is just kind of a summary slide for cations. I started with cations and talked about the main group metals and the transition metals. So cations are almost always metals. So our main group metals almost always, or always probably, have a positive charge equal to their group number. It's also equal to the number of valence electrons that they have. So if we think about our group 1 elements, like lithium, for example, lithium is in group 1, so it's likely to form a +1 ion. So lithium +1 is the ion that will form from lithium, and that +1, so that comes from the group number, and also we know that there is only one valence electron in lithium because its electron configuration could be written as helium 2s1. So it's that one valence electron in the n=2 shell. All right, so we've got some weird things happening in groups 13, 14, and 15. So those are, if we're looking at period 2, that's boron, carbon, and nitrogen. So some of them may form cations with various charges, but aluminum is always +3. So that's the only one you have to remember from that area of the periodic table, from group 13, is aluminum. It's always +3. And like we just saw from the electron configuration of iron, transition metals can be found as several types of cations. So they can have lots of different charges in nature. Because their electron configurations allow them to be kind of flexible. We take away those 4s electrons and we get one type of ion, but then we keep taking away d electrons and we can get half-filled subshells or something like that. So that's why we have various forms of transition metal cations. So you don't have to remember those, but I just put them here because I wanted to show you how pretty they are. Transition metals are really pretty, these ions in solution. All right, so we talked about cations. Let's talk about anions. I know your book doesn't do it this way, but I think we start there, and then anions are going to be easy because it's just going to be the opposite. So instead of thinking of ionization energy, let's think of electron affinities instead. Chlorine has a really strong first electron affinity so it's a very positive electron affinity, which means it's easy to add an electron. So it has a strong affinity for electrons, so it wants you to give it an electron. That's why chlorine is typically found as a +1 anion. So we can look at the electron configuration and easily see why. So if we add an electron to our 3p subshell, we end up with an we end up being isoelectronic with a noble gas. So chlorine is isoelectronic with argon, as we saw in our first practice problem today, actually. So that is why chlorine is likely to be found as a -1 anion, because it likes to have that noble gas configuration. So adding that electron is super easy. It's super favorable, actually, for chlorine to form that -1 anion. What about when we add another one? Well, now let's look at sulfur. Sulfur's next to chlorine. So sulfur is one further. It's in group 16 instead of group 17. Sulfur has a strong second electron affinity. So it's easy to add a second electron to sulfur, which is why sulfur is typically found as a -2 anion. So is oxygen. Anything in group 16 really is likely to be found as a -2 anion because of this, because it has a strong second electron affinity and because of its electron configuration. So let's look at it. So we add these 2 electrons to sulfur and we end up with our nice filled subshell. So we So sulfur 2-, our sulfur anion, is isoelectronic again with argon and with our chlorine -1 ion. So we're again isoelectronic with a noble gas, and that's why it's likely to be found that way. It's favorable to become a noble gas configuration. But adding a third one would be super hard. If you look at the electron affinity, the third electron affinity of sulfur, it's going to be a negative number probably. Because if we tried to add in this 4s electron, you'd be adding an electron to a whole nother shell of a whole nother electron shell, and that's bad. So sulfur is not found as a -3 anion. We can't add 3. We can add 2 very easily. So just to summarize, the charge of the anion is directly related to electron configuration, just like the charge of the cation was directly related to electron configuration. You can draw these orbitals and you can easily deduce what kind of ion is likely to form based on what orbitals need to be filled or what orbitals need to be emptied if we're talking about cations. So focusing on anions, vacancies in the p subshells allow for atoms to gain electrons. So sulfur here, for example, has 2 vacancies. There's the potential for 2 more electrons to be in that 3p subshell. So it has 2 vacancies, and that is what allows for sulfur to gain 2 electrons. And chlorine was very similar. It had 1 vacancy, so it wanted to gain 1 electron. So let me rewrite these, 15, 16, and 17. These usually have a negative charge equal to 18 minus the group number. So if we're talking about chlorine, chlorine is in group 17. So chlorine has a charge equal to, negative charge equal to 18 minus 17. So it has a -1 charge. You might want to write it as the group number minus 18 instead. Then you don't have to remember that it's negative. It just will be negative by definition. So chlorine is likely to be found as this -1 charge because group 17 minus 18 gives us a -1. That's also equal to the number of vacancies in the p subshell. Chlorine has 1 vacancy in the p subshell. It forms a -1 anion. Sulfur has 2 vacancies in the p subshell. It forms a -2 anion. Group 15 is not always as reliable. Nitrogen and phosphorus tend to be -3 ions, but not always. So you don't need to worry about those most of the time. Other nonmetals like hydrogen and group 14 elements, so that's like carbon. Carbon is a group 14 element. They can form cations or anions, and there's not really a rule that goes either which way for those, because I showed you hydrogen could be a +1 cation or a -1 anion if it goes to having no electrons or being isoelectronic with helium. So these are 2 compounds made out of those ions. So we got hydrochloric acid, which comes from an H+ ion, and we've got cupric hydride, copper hydride, which comes from the -1. Because copper is a metal, metals are almost always, if not always, positively charged. So that means the hydrogen has to be negatively charged so that we have a balanced compound. But we'll get into that more in the next chapter. Carbon and silicon likewise can be +4 or -4 because they're in that group 14. All right, cool. Here's another practice question for you. What's the electron configuration for the P3- ion? So phosphorus 3- ion. So I'll let you guys practice this at home. I'm gonna give you the answer real quick. So phosphorus is number 15. So we've got neon as our noble gas core. And then, so I'm going to add electrons to it. Start with the phosphorus atom itself, and then add electrons to it. So we've got neon, and then we've got 3s2 electrons, and we've got 3p3 electrons. So that's the electron configuration for phosphorus atom. So now we're going to add 3 electrons because we need a negatively charged ion. So we add 3 negatively charged electrons to this. And that's going to get us to 3p6. But we're probably not going to write it that way. We'd actually write it with the next noble gas core because phosphorus 3- ion is isoelectronic with argon, which is isoelectronic with the chlorine and sulfur ions that we talked about just now. Cool. So you could write it like this. You could write it with the 3s2, 3p6. That's usually more appropriate if you have all of the numbers that come before that. The 1s2, 2s2, 2p6 would be an okay way to write it, but this is definitely faster, right? So the electron configuration in noble gas notation for the phosphorus anion is argon by itself, just argon. Cool. All right, so now we're going to talk a tiny bit about ionic radius. So this is going to go pretty fast, so don't worry. The radius of a cation or an anion is called its ionic radius. So the ionic radius of elements is different than their atomic radius. The atomic radius is for the neutral atom. The ionic radius is going to be different. So, for example, cations are smaller than the atoms from which they're formed. Forming a cation requires the loss of an electron. So we're decreasing electron-electron repulsion. We're getting rid of one of our valence electrons. So that means that there's less electron-electron repulsion and the less screening, so the electrons can be drawn closer to the nucleus, which makes the cation smaller. Some particular examples would be with sodium. Sodium, when it becomes an ion, the +1 ion, it loses its 3s electron. And that means it lost a whole extra electron shell. So the sodium plus ion is a lot smaller than the sodium atom itself. Okay? It goes the opposite way for anions. Anions are larger than the atoms from which they're formed. Oops, that should be an anion, sorry. Forming an anion requires gaining an electron, which means that we're increasing electron-electron repulsion, we're increasing electron shielding, which means the electrons don't feel the nucleus as strongly, and they aren't pulled in. They actually make the atom bigger when we have more electrons. It could go the same way as this, so they didn't have a figure of this in your book, but it could go the same way if you have, for example, fluorine. Fluorine -1 has a 1s2, 2s2, 2p5, and if we add an electron to that, we're going to make it bigger because now we're going to have a 2p6 in there. We're going to have an extra electron floating around. So it's easier to see with the cations for sure because they actually change the shell of the shell size of the atom or ion, whereas the anions, it's not as easy to see, but just remember one and you'll remember the opposite one. This is a picture of ionic radius versus atomic radius. So the atomic radius is the dashed line, and the ionic radius is the sphere, the color sphere. Okay, shows you that concept pretty well, I think. And finally, we're going to talk a little bit about isoelectronic series. That means it's a series of two or more species that have identical electron configurations. So isoelectronic, same number of electrons. So they have the same electron configurations, but they have different nuclear charges. So let's look at oxygen, fluorine, and neon. The oxygen anion has 8 protons in its nucleus because it's number 8 on the periodic table, but it has 10 electrons because it's an ion. Fluorine has 9 protons in its nucleus because it is number 9 on the periodic table, and it has 10 electrons because it's an ion. And neon has 10 and 10 because neon's a neutral atom. So you can see as we go across this isoelectronic series, we're getting smaller. So the more protons we have when we're talking about the same number of electrons, the more protons we have, the smaller the ionic or atomic radius. So here's what you need to remember. With isoelectronic species, the number of protons dictates the size. The less protons there are, the bigger the ion. The more protons there are, the smaller the ion. So it's kind of the opposite of what we said about adding or taking away electrons. If we have more protons, that means they're pulling those electrons in closer and making the ion smaller. If there's less protons, they aren't pulling it in as far, making the ion bigger. And then this is a table that shows you the ionic radius or atomic, well, they're all ionic in this case. The ionic radius of these isoelectronic species, these are all isoelectronic with neon, and you can see they have the same number of electrons, same electron configuration, but because they have different numbers of protons, they have different ionic radii, sorry. And the magnesium ion is the smallest one because it has the most protons. All right. And here's another practice question for you guys. We're going to list the following ions in order of increasing ionic radius. So first we're going to see, are they all isoelectronic? If they are, then we just need to look at the number of protons. So nitrogen is 3 away from neon. So if it's a -3 ion, it goes to neon. Oxygen is -2. If it gets 2 electrons, it goes to neon. Cool. Fluorine is -1. If it gets 1 electron, it goes to neon. Sodium is +1, so it loses an electron, goes back to neon. And magnesium is +2. It lost 2 electrons and went back to neon. So they all have 10 electrons, just like our previous table and picture. So it just depends on the number of protons. So we just have to look at the atomic numbers. So nitrogen is 7, oxygen is 8, fluorine is 9, sodium is 11, and magnesium is 12. So the smallest one is going to be magnesium, and then sodium. So we're going to have kind of a backwards number line, going positive to negative instead. And these are less than signs because I'm talking about the size of the radius. The size of the radius is increasing as we go to the right. Magnesium is the smallest. And then nitrogen is the biggest. And that's it. I'll see you guys tomorrow.